excited to bring today a return speaker. Arjun Ayyangar is a volunteer for NASA Solar System Ambassador Program since 2018. He did a talk for us last year on black holes, which was really, really interesting. He's got a master's degree in computational sciences and robotics from South Dakota School of Mines and Technology, another master's degree in computer science from Georgia Institute of Technology, and he currently works as a systems engineer at Lockheed Martin. So he brings a lot of knowledge with him today, and he's going to do a talk for us on the James Webb Telescope and other and other interesting fun facts. So please welcome him.
Thank you so much.
Good.
Yep. I'm Arjun Ayyangar. I'm living in Mount Laurel, New Jersey, in the United States. And I will go ahead and share my screen and begin with the presentation about the James Webb Space Telescope. So thanks everyone for coming. This topic is about the James Webb Space Telescope. Um, Before I begin, as mentioned previously, got two master's degrees and currently working at Lockheed Martin, New Jersey. And I'm also a musician and play the piano, harp, the organ, and the Persian santur and veena, which is an Indian instrument. I have my YouTube site listed here. I'm currently pursuing music studies at Berklee College Online, and I'm also a Goodwill Ambassador for Empower the Children, which is a New Jersey registered charity organization which helps disadvantaged people in Calcutta, India, and other parts of the world. I've been a NASA Solar System Ambassador volunteer since 2018, and I guess we'll begin with the presentation. So first, we will go over the history of James Webb Space Telescope and its missions. Who is James Webb? James Webb headed NASA from 1961 to 1968. As early as 1965, James Webb had written that a major space telescope, then known as the Large Space Telescope, should become a major NASA effort. This telescope was later named after James Webb. He created the NASA University program, which established grants for space research, and he laid the foundations at NASA for one of the most successful periods of astronomical discovery. The James Webb Space Telescope is an infrared space observatory and the biggest astronomical space science telescope ever built. Launched on December 25th, 2021, it will study every phase in the history of our universe. It is the impressive result of efforts from NASA, the European Space Agency, and the Canadian Space Agency. JWST has the ability to look back in time to the early universe and see some of the first galaxies and stars. Webb has four mission science goals. Search for the first galaxies or luminous objects that formed after the Big Bang. Determine how galaxies evolved from their formation until the present. Observe the formation of stars from the first stages to the formation of planetary systems, and measure the physical and chemical properties of planetary systems and investigate the potential for life in those systems. What can Webb observe? Webb will conduct deep-wide surveys of galaxies in the rest-frame optical and near-infrared and observe the birth of stars in the planetary system. NASA leads an international partnership in the joint JWST mission that includes the European Space Agency and Canadian Space Agency. NASA provides overall responsibility for the Webb mission. ESA, or European Space Agency, provides the near-infrared spectrograph, mid-infrared instrument optics assembly, and the Ariane launch vehicle. CSA, or the Canadian Space Agency, provides the fine guidance sensor and near-infrared imager and slitless spectrograph. Many NASA centers manage different aspects of JWST. Goddard Space Flight Center manages the Webb project. Jet Propulsion Laboratory manages the Mid-Infrared Instrument. Ames Research Center provides detector technology development. Johnson Space Center provides observatory test facilities. Marshall Space Flight Center provides mirror technology development and environmental research. Glenn Research Center provides cryogenic component development. The academic and industry partners are Ball Aerospace, Harris Corporation, Lockheed Martin, Northrop Grumman Aerospace Systems, the Space Telescope Science Institute, and the University of Arizona. JWST program has 3 segments: Launcher segment, which is for launching into orbit, Observatory segment, which is for observing the galaxies, and Ground segment, which is for communicating with the telescope. The James Webb Space Telescope is an international project led by NASA with its partners ESA and CSA. It was launched on December 25, 2021 on an Ariane 5 rocket from Europe's spaceport in Kourou, French Guiana. Why from French Guiana? This is because it's launched near the equator, taking advantage of Earth's greater rotation speed there to boost launch performance. JWST telescope is orbiting the Sun at 1 million miles away from Earth. The rocket travels for 30 days before releasing the telescope on January 24, 2022 into orbit. At launch, Hubble weighed 25,000 pounds. James Webb only weighed 14,400 pounds. This is due to the requirements of the rocket used from both a weight and a size perspective. Here is a simulation video of the space rocket launch. It was created before the launch but gives a very good simulation.
The James Webb Space Telescope, NASA's #1 science priority. The Webb telescope is designed to look back to a time when stars and galaxies were first forming, over 13.5 billion years ago. With its revolutionary design and capabilities, the Webb telescope is about to unleash a new dawn of discovery.
À tous de vidéo, attention pour le décompte final. 10, 9, 8.
Seconds before liftoff, the Ariane 5's liquid-fueled engine comes to full power, followed by the ignition of the 2 solid rockets. We have liftoff. The Webb telescope is finally on its way, the result of years of study and development by thousands of team members in the United States, Canada, and Europe. Webb's spacecraft ascends nearly vertically through the heavy lower atmosphere of Earth. As the rocket reaches maximum acceleration, the spent solid rocket motors are jettisoned safely into the Atlantic Ocean. Reaching the upper atmosphere where protection is no longer needed, the payload fairing is jettisoned and falls away. Accelerating through the atmosphere, the Ariane 5 rocket's first stage expends its fuel and shuts down. The empty first stage then separates from the upper stage. After first stage separation and before second stage ignition, the Webb telescope has a slightly downward trajectory as it speeds over the Atlantic Ocean. The upper stage motor ignites and the ascent to L2 resumes, never again to be interrupted. The exposed telescope is delicate and must be protected from the sun's fierce heat. To avoid overheating and damage, a carefully designed series of oscillations are performed that provide the necessary protection. Near the end of powered flight, the roll program stops and the launcher then assumes the proper attitude for separation. After separation from the Aryan upper stage, the Webb telescope continues its journey to L2 under its own power, taking the next step to its final orbital station 1 million miles from Earth. The Webb telescope is about to unleash a new dawn of discovery.
Here is an image showing JWST's instruments. The telescope's 4 instruments, cameras, and spectrometers have detectors that are able to record extremely faint signals. The space-based portion of the James Webb Space Telescope system consists of 3 parts: Integrated Science Instrument Module, or ISIM, which is the heart of the observatory; Optical Telescope Element, or OTE, which is the eye of the observatory, which includes the mirrors and backplane; and Spacecraft Element, which is the support functions for the operation of the observatory, which includes the spacecraft bus and the sun shield. We will go through each of these parts in greater detail. The Optical Telescope Element, or OTE, is the eye of the James Webb Space Telescope Observatory. The OTE gathers the light coming from space and provides it to the science instruments. The OTE is made up of a 6.5 meter diameter primary mirror made of 18 hexagonal segments, a round 0.74 meter secondary mirror, and a tertiary mirror. Comparing JWST with Hubble mirrors, the Hubble mirror is made of ultra-low expansion glass, while JWST mirror is made of ultra-lightweight beryllium. The Hubble mirror coated with aluminum and magnesium fluoride to reflect ultraviolet light, while JWST mirror is coated with gold to reflect infrared light. JWST has a primary mirror made of 18 separate segments that unfold and adjust to shape after launch. Here's a video on a deployment animation with me playing Star Wars theme song in the background. Next, we will talk about the wavelength, size, orbit, and distance for JWST, a successor to Hubble. With infrared reflection, we see more stars than with visible light reflection. Webb primarily looks for objects in the infrared, while Hubble looks primarily for objects in the visible and ultraviolet range. The ever-expanding universe results in extension of the wavelength, so the light emitted by far-off galaxies are infrared wavelengths. Here is the size comparison of Webb and Hubble's mirror. Note the human reference at the bottom for scale. The Earth is 93 million miles from the Sun, and the Moon orbits the Earth at a distance of approximately 238,855 miles. The Hubble Space Telescope orbits around the Earth at an altitude of 350 miles above it. Webb does not orbit the Earth. Instead, it sits at the Earth-Sun Lagrange L2 point, which is 1 million miles away. As the Earth orbits the Sun, Webb orbits with it, but stays fixed in the same spot with relation to the Earth and the Sun. This illustration compares various telescopes and how far back they are able to see. Essentially, Hubble can see the equivalent of toddler galaxies, and Webb telescope can see baby galaxies. One reason Webb will be able to see the first galaxies is because it is an infrared telescope. Herschel telescope is also an infrared telescope that was built by European Space Agency. It was active from 2009 to 2013. Herschel looked for the most actively star-forming galaxies, which emit most of their energy in the far infrared. Webb will find the first galaxies to form in the early universe. It needs extreme sensitivity in the near infrared. Why mirrors and not lenses? The number one benefit of using mirrors is that they are not heavy. Since they are much lighter than lenses, mirrors are a lot easier to launch into space. Mirrors use reflection instead of refraction. This results in accurate images as photons are not lost. Here's a video on JWST's mirror coding.
Mirrors on a telescope are often coated with some kind of metal in order to reflect as much light as possible. Now, the type of metal depends upon the kind of light the telescope is looking at. The James Webb Space Telescope is looking at infrared light, and for that, gold is the ideal choice. To find out how the gold is put onto the mirrors of the James Webb Space Telescope, we're here at Quantum Coating in Moorestown, New Jersey. So Ian, how much gold are we talking about? Enough for a ring?
Not even that. Well, it depends on how big your ring is, of course. But the thickness of the coating is almost unimaginably small. To give an example, this piece of paper is about 1/1000th of an inch. We could take 1,000 gold coatings, stack them all side by side, and they would be the thickness of this piece of paper. In terms of the amount of gold that we need, it comes to 3 grams of material.
Okay, and 3 grams looks like
3 grams I have
this. Wow, that's amazing, considering how big the mirror is.
That amount, when it's spread out thin enough, covers the whole surface of the hexagon.
When you apply the coating, are we talking about like a paint job?
No, this is called vacuum deposition. It happens in a chamber where all of the air has been sucked out to create a vacuum. Then we vaporize the gold. We create a cloud of vapor, and that vapor condenses on the surface to form the film.
And why do you choose to apply the gold that way?
That's the way to get the maximum reflection. Spray painting or other techniques wouldn't give us enough reflection.
And can we actually see the gold being applied to a mirror?
Sure. Ty's the guy who operates the coding machine. He'd be happy to show you how that works.
Hey, Ty.
Hey, how you doing, Mary?
I was told that a coding process is about to start.
Sure, we're about to start the coding soon.
Can we tag along?
Sure. Okay, see, what we're doing here now, we're preparing the mirror for coding, cleaning the mirror of any contaminants or any particles that could be on the mirror.
So, Ty, what's going on here now?
Okay, well now we're putting on the shield and the mask for the mirror. The coating cannot be beyond a certain area on the mirror.
So you want the gold to just be on the surface, nothing on the sides or anything?
Right. There's a bevel also on the edge of the mirror. We don't want any coating on the bevel either.
How long is this going to take?
Maybe an hour in total.
I understand there are no cameras in the chamber. Can we see what's going on?
We take a look inside our viewport. We see the part rotating and we can see the glow disperse right now.
So, Ty, we couldn't show the actual company-specific equipment that was used to apply the coating, but we get to see the gold-coated mirror fresh out of the chamber.
Yeah, that's neat. Look at it. The mirror's coated now. We're all complete and we're ready to ship it off to the customer and they can begin their testing.
Well, thanks so much for guiding us through your coding process. It was fascinating.
Well, not a problem at all.
As you can see, gold isn't just a fashion accessory for the James Webb Space Telescope, but a critical addition to making the telescope work its very best. Thanks for joining us for another edition of Behind the Webb.
Next, we will talk about the instruments of JWST in depth. Integrating 4 major instruments and numerous subsystems into one payload, the ISIM, is a daunting endeavor. To simplify integration, engineers have divided the ISIM into 3 regions. The Region 1 component is the cryogenic instrument module. This chills the detectors down to 39 Kelvin. The Region 2 component is the ISIM electronics compartment, which provides the mounting surfaces and ambient thermally controlled environment for the instrument control electronics. The Region 3 component, located within the spacecraft bus, is the ISIM command and data handling subsystem, with integral ISIM flight software and the MIRI cryocooler compressor and control electronics. We will cover the MIRI and other instruments in more detail in a later slide. This is a picture of how the 4 instruments fit together in the ISIM, which we saw in the previous slide. We will go through each of them. The near-infrared camera, or NIRCam, is Webb's primary imager that will cover the infrared wavelength range 0.6 to 5 microns. NIRCam will detect light from the earliest stars and galaxies in the process of formation, the population of stars in nearby galaxies, as well as young stars in the Milky Way and Kuiper Belt objects. NIRCam is equipped with coronagraphs, instruments that allow astronomers to take pictures of very faint objects around a central bright object like stellar systems. NIRCam's coronagraphs work by blocking a brighter object's light, making it possible to view the dimmer object nearby. NIRCam was built by University of Arizona and Lockheed Martin. The Near-Infrared Spectrograph, or NIRSpec, has programmable microshutters which enable observation of up to 100 objects simultaneously. NIRSpec will operate over a wavelength range of 0.6 to 5 microns. Analyzing the spectrum of an object can tell us about its physical properties, including temperature, mass, and chemical composition. The atoms and molecules in the object imprint lines on its spectrum that uniquely fingerprint each chemical element present and can reveal a wealth of information about physical conditions in the objects. The NIRS spec is designed to observe 100 objects simultaneously. The NIRS spec will be the first spectrograph in space that has the remarkable multi-object capability using a microshutter array. NIRS spec's microshutter cells, each approximately as wide as a human hair, have lids that open and close when a magnetic field is applied. Each cell can be controlled individually, allowing it to be opened or closed to view or block a portion of the sky. NIRSpec is a contribution of the European Space Agency and is built by Astram together with a group of European subcontractors. Mid-infrared instrument, or MIRI, covers the wavelength range of 5 to 28 microns. Its sensitive detectors will allow it to see the redshifted light of distant galaxies, newly forming stars, and faintly visible comets, as well as objects in the Kuiper belt. The spectrograph will enable medium-resolution spectroscopy, providing new physical details of the distant objects it will observe. MIRI was built for ESA by a European consortium of 10 countries. The Fine Guidance Sensor, or FGS, allows Webb to point precisely so that it can obtain high-quality images. FGS is a guider, which helps point the telescope. The near-infrared imager and slitless spectrograph will be used to investigate first light detection, exoplanet detection and characterization, and exoplanet transit spectroscopy. NIRISS has a wavelength range of 0.8 to 5 microns and is a specialized instrument with these main modes, each of which addresses a separate wavelength range. FGS and NIRISS were built by the Canadian Space Agency. The spacecraft element consists of the tennis court-sized sunshield designed by Northrop Grumman and the spacecraft bus, which houses the flight avionics, power system, and solar panels. Because of Webb's large size, engineers had to design components that fold origami style into the Ariane 5 rocket's fairing configuration. What's a bus without steering? So the spacecraft bus houses the steering and control electronics, including the computer and the recreation wheels. The Region 3 component located within the spacecraft bus is the ISIM command and data handling subsystem, which integral ISIM flight software and the MIRI cryocooler compressor and control electronics. The bus is home for 6 major subsystems: electrical power subsystem, attitude control subsystem, communication subsystem command, data handling subsystem, propulsion subsystem, and thermal control subsystem. The James Webb Space Telescope's backplane is the large structure that holds and supports the big hexagonal mirrors of the telescope. The backplane has an important job as it must carry not only the 6.5 meter diameter primary mirror plus other telescope optics, but also the entire module of scientific instruments. Webb's biggest feature is a tennis court-sized 5-layer sunshield that attenuates heat from the sun more than 1 million times. The James Webb Space Telescope will observe primarily the infrared light from faint and very distant objects. In order to be able to detect those faint heat signals, the telescope itself must be kept extremely cold. To protect the telescope from external sources of light and heat like the sun, earth, and moon, as well as heat emitted by the observatory itself, Webb has a 5-layer tennis court-sized sunshield that acts like a parasol providing shade. Its actual dimensions are 69.5 feet by 46.5 feet. The sunshield will allow the telescope to cool to negative 370 degrees Fahrenheit. This sunshield will always be between the sun, earth, moon, and the telescope. It's able to be positioned this way because JWST will be orbiting the Sun 1 million miles away from, but approximately in line with the Earth. The Sun shield is made of the polyimide film Kapton, which is stable at very low temperatures. The core material of the Sun shield is the material Kapton is coated with, which is aluminum, and the two closest layers to the Sun are also doped with silicon. Each layer of the Sun shield is incredibly thin. Layer 1 will face the Sun and is only 0.002 inches thick, while the other four layers are 0.001 inches. The thickness of the aluminum and silicon coatings are even smaller. The silicon coating is 1.9 microinches thick, while the aluminum coating is about 3.93 microinches thick. By necessity, MIRI's detectors need to be at a temperature of less than 7 Kelvin to operate properly. This temperature is not possible on Webb by sunshield alone. So Webb carries a cryocooler that is dedicated to cooling MIRI's detectors. The cryocooler will allow the telescope to cool to negative 447 degrees Fahrenheit for MIRI. The cryocooler is located in the heart of the spacecraft bus, or the sun-facing warm side of the observatory. It has very low vibration in order to avoid induced shaking of the optics and resultant blurred images. Being a refrigerator and a closed system, the cryocooler does not consume coolant like an ice chest full of ice or a big container of liquid helium. So its life is limited only by wear in its moving part or the longevity of its electronics, all of which should last for many years. The Earth's pointing antenna sends science data back to Earth and receives commands from NASA's Deep Space Network. Always facing the sun, panels convert sunlight to electricity to power the observatory. NASA's Deep Space Network is an international network of antennas that provide communication links between planetary exploration spacecraft and their mission teams on Earth. The Deep Space Network consists of three deep space communications complexes placed at approximately 120 degrees apart around the world, at Goldstone in California's Mojave Desert, near Madrid, Spain, and near Canberra, Australia. This strategic placement permits constant links to distant spacecraft even as the Earth rotates on its own axis. Star trackers are small telescopes that use star patterns to target the observatory. It is an optical device that measures the positions of stars using photocells or a camera. As the positions of many stars have been measured by astronomers to a high degree of accuracy, a star tracker on a satellite or spacecraft may be used to determine the orientation of the spacecraft with respect to the stars. In order to do this, the star tracker must obtain an image of the stars, measure their apparent position in the reference frame of the spacecraft, and identify the stars so their position can be compared with their known absolute position from a star catalog. A star tracker may include a processor to identify stars by comparing the pattern of observed stars with the known pattern of stars in the sky. Without accurate star trackers, a spacecraft would lose its way in space. President Joe Biden released this deep field image on July 11, 2022, the first scientific view from Webb revealed publicly. What you see here is the image of galaxy cluster SMACS 0723, also known as Webb's first deep field, as it appeared 4.6 billion years ago. This image covers a patch of sky approximately the size of a grain of sand held at arm's length and reveals thousands of galaxies in a tiny sliver of the vast universe. We are looking back in time to within a billion years after the Big Bang. This image is a visual grouping of 5 galaxies called Stephan's Quintet. This is the Webb's largest image to date, covering about 1/5 of the Moon's diameter. This image helps astronomers witness the merging and interactions between galaxies. Stephan's Quintet was discovered in 1877 by the French astronomer Edouard Stephan. This is the image of the Southern Ring Planetary Nebula, catalogued as NGC 3132. Planetary nebulae are shells of gas and dust ejected from dying stars. NGC 3132 is approximately 2,500 light-years away. This is the image of WASP 96b, one of the more than 5,000 exoplanets in Milky Way. It is located 1,150 light-years away. It is an ideal target for atmospheric observations. The telescope has captured the distinct signature of water, along with evidence for clouds and haze, in the atmosphere surrounding this hot, puffy gas giant planet orbiting a distant sun-like star. The landscape of mountains and valleys speckled with glittering stars is actually the edge of a nearby young star-forming region called NGC 3234 in the Carina Nebula. Captured in infrared light, this image reveals for the first time previously invisible areas of star birth. Next, we will discuss 4 revelations from the Webb. In its first observing programs, which kicked off in June of 2022, Webb discovered many distant galaxies that lie beyond the reach of the other observatories, such as Hubble Space Telescope. The telescope is well suited to spotting galaxies that formed early in the universe's history, since it can detect infrared light. Many research teams are racing to identify the most distant galaxy in the Webb data. Several candidates have been spotted that will need to be confirmed through further studies. Once confirmed, this will break Hubble's record for the most distant galaxy, which dates to around 400 million years after the Big Bang. Webb's distant galaxies are also turning out to have more structure than astronomers had expected. One study of Webb's first deep field image found a surprisingly large number of distant galaxies that are shaped like disks. Using Hubble, astronomers had concluded that distant galaxies are more irregularly shaped than nearby ones, which, like the Milky Way, often display regular forms such as disks. The theory was that early galaxies were more often distorted by interactions with nearby galaxies. But the Webb observation suggests that there are up to 10 times as many distant disk-shaped galaxies as previously thought. At the infrared wavelengths detected by Webb, most of the massive galaxies looked much smaller than they did in Hubble images. Hubble studies suggested that galaxies start out small and grow bigger over time, but the Webb findings hint that Hubble did not have the whole picture, and so galactic evolution might be more complicated than scientists had anticipated. A new investigation with NASA's James Webb Space Telescope into K2-18b, an exoplanet 8.6 times as massive as Earth, has revealed the presence of carbon-bearing molecules, including methane and carbon dioxide. Observations from JWST also provided a possible detection of a molecule, dimethyl sulfide, or DMS, and compound dimethyl disulfide, or DMDS. On Earth, DMS is only produced by life. The bulk of the DMS in Earth's atmosphere is emitted from phytoplankton and marine environments. On Earth, DMDS is produced by natural and industrial resources. Finding DMS and DMDS in K2-18b could indicate potential life there. Here's a video that summarizes what we talked about, along with me playing Mozart's Twinkle Variations in the background. This brings us to the end of the presentation. For more information on JWST, you can visit the NASA website, nasa.gov/web first images. NASA also has a podcast called Curious in Universe. Before we move into questions, I have a quiz for everyone. Feel free to shout out the answers or put in the responses in the chat. So yeah, the first question, the Earth's rotation speed is highest at where? The poles, the equator, or Rapid City? Everybody's saying equator. Yep, equator it is. Yep. How long did the rocket travel before releasing telescope to orbit? 30 days, 30 hours, or 30 weeks? Right? A few people are responding. 30 days. Yep, that's what it is. How thick is each layer of sunshield? 0.001 to 0.002 inches, 0.01 to 0.02 inches, or 0.1 to 0.2 inches? Okay, let's see if anyone responds. Yep, a few people are responding. Yep, so it's the first one. 0.001 to 0.002 inches. In orbit, JWST gets its energy from what? Wind, solar power array, or lithium batteries? Okay, I see people responding. Yes, solar power array. JWST mirrors are coated with what? Silver, gold, or diamond? Yep, gold. JWST mirrors reflect what? Visible light, ultraviolet light, or infrared light? Yep, I see a bunch of people responding. Infrared light is the answer. How many miles away from Earth is JWST orbiting the Sun? 1 million, 10 million, or 100,000? One million. Yep, that's right. JWST's sunshield size is the size of what? Tennis court, ping pong table, or coffee table? Tennis court. That's right. JWST primary mirror diameter is what? 3.5 feet, 6.5 meters, or 6.5 feet? Okay, looks like we have people responding. 6.5 meters is right. JWST mirrors are made up of what? Beryllium, aluminum, or glass? Yep, beryllium. Sunshield is coated with what? Aluminum, beryllium, or glass? Yep, I think I feel a few people are responding. Yep, aluminum is the answer. Sunshield is made up of what? Glass, Kapton, or Krypton? Sunshield. Sunshield, what is it made up of? Yep. Yep, I think I see a few people responding. Yep, Kapton. The sunshield will allow the telescope to cool down to what? Negative 70 degrees Fahrenheit, negative 370 degrees Fahrenheit, or negative 37 degrees Fahrenheit? Okay, I think we have a few people responding. The correct answer is the second one, negative 370 degrees Fahrenheit. How much gold is used for coating the mirrors? 3 kilograms, 30 grams, or 3 grams? All right, so it looks like a bunch of people responded. It is 3 grams. How much does Webb weigh? 14,300 pounds, 1,430 pounds, or 143 pounds? Yep, so it's 14,300 pounds. All right, here are the references used. And yeah, does anyone have any questions? I think a few people might have asked something in the chat, so I don't know if we want to look at those first.
Yeah, that would be great.
Okay, let me look at the chat to see what people had. Okay, beautiful. Okay. Okay, global project.
I
Let me.
have a
Okay. Yeah,
question
your
about
question?
the okay.
Yeah, go ahead with your question. Yeah, whoever's asking. I don't see much questions here in the chat. I think it's okay. Is there a way to do maintenance of the telescope? Is that the question you're asking about?
Yeah, I have a question about the gold coating because it's awfully thin, and is there a risk of damage with I don't know, micrometeorites, space dust, or whatever? And in this case, the quality of images will be at risk or not?
I don't think the gold coating affects the images. The gold coating is mainly just for the telescope's ability to observe the universe in infrared light. So I think gold coating is actually helpful for infrared light. I don't know of any issues for that affecting like the images that get received because they say gold is an infrared light reflector.
Thank you.
Yep. Um, Let me look at the chat. Okay, I think okay, is there any way to do maintenance on the telescope? Um, Doing maintenance on the telescope, I'm not sure if there's a specific method. I know that there's communication with the deep space network and everything. So I think as long as it's in orbit, um, signals can be processed from there. But I don't know if any specific maintenance is being done from time to time. I think it's just the results are just based off of like the camera and what you can see from signals that come back to Earth to see how good it is. And I think if the signals are not that good, then a new telescope might need to be sent out to replace JWST eventually. Let's see, any other questions in the chat? Lagrange 2, does it still need to make the occasional burn to maintain position? Um, I don't think so. I think once it's in position, it's just going to be in orbit, just like the Earth orbits around the sun. I don't think it needs to make the occasional burn for maintaining position. So yeah, I think that covered all the questions here. Oh, somebody asked, is when you say the width of a human hair, how wide is that? Um, Average human hair. That's a good question. Let me see. Okay, average human hair for JWST. Okay, so the primary mirror is aligned to focal point with accuracy of 1/10,000th of thickness of a human hair. What is the average? Let me see. Human hair. I think, yeah, I mean that's true. Like how JWST calculates it might vary, but I think it's based off of the average, which is the length. I think it's in micro inches, so it's average length of hair is between 15 to 17 inches. I'm assuming this is based off of like probably the lower end, so I would say it's close to like 15 inches is what it's measuring here when they talk about average human hair. What other questions here? How long is JWST expected to last? Okay, JWST. I mean, it's been there for quite a while. I think it's going to be at least another um, 5 to 10 years because it says it's between 20. It was originally expected to last only 10 years, but it's actually lasting more than 20 years. So I think it's going to be there for at least another 5 to 10 years left, so, as far as things are concerned. Okay, so exoplanet that had life indicators discovered. How much in the past would that be? How far are we looking back in time? So some of these galaxies and these images are like looking back even billions of years ago because that's how the infrared um, is coming. The K2 18b planet, I think that's not that old. K2 18b is about is located about 124 light years away. So I don't probably like in the hundreds because um 124 light years wouldn't give us that much of a distant past. So it's towards like the hundreds years. Okay, the next question seems like what is the redshift of the more distant objects? What's the redshift of the more distant objects? Uh, Redshift is mainly how like infrared light gets reflected. So that is dependent on more distant objects. If there's more distant objects, there'll be greater the shift. So, and I think infrared objects that are far away would be shifting into more, um, and that shift is used to determine like how far the galaxies were from Earth and how much back in time you need to go. So I think yeah, I think that covered all the questions. Did anyone else on the line have any more questions?
Arjun, if you'd like to stop sharing your screen, and then if anybody, we can see the gallery, and if anybody has a question they want to ask, they could raise their hand. That would be cool.
Sure, I can do that.
See if there's any hands raised. I'm going to ask a question here. Um, I was I was absolutely blown away. I mean, you gave such a wonderful presentation, and looking at how this was put together and the details, and I know it's just the surface of it. Um, I'm wondering about, if you know this, like how many points of failure did they have to consider when they were building this and designing it?
Not sure about the specific points of failure, but it was definitely a big effort and like a lot of planning, and I think it was even might have even been postponed like the launch date originally because they needed to make sure it was all in shape. But yeah, it was a pretty big effort. I think they were thinking of all the possible. As far as I've heard, I don't think there was any specific failure that happened after it had launched, but the launch date was like postponed for a few years until it was ready to launch type of thing. I think it was supposed to be like 2018 or 2019, but it actually launched only in 2022 because they had to confirm that everything is working.
It
Was it
seems like there's just so many possibilities of something
right? Right.
that could go wrong, and is it gonna make the whole thing not work? I don't know. It's
Right.
just mind blowing to me.
Yeah, yeah, that's a good thing. Yeah.
Anyone have any questions? Feel free to raise your hand. Eric, of course.
Yeah, of
Always got,
course.
he's always got good questions.
All right. So I was thinking about the design of the telescope,
Uh-huh.
and sorry, um, there's the range of I'm running into the limits of my education here. I got a computer science degree, and I'm talking about astronomy here. So the actual wavelengths that we're interested in might be here, but the James Webb Telescope might have to broaden that
Right.
in order to compensate for redshift. Because if something, I'm gonna make up a color. Um, let's say, okay, just pick red. By the time it gets to us, it might have been shifted like so let me, or it'll do it like this, down to here. I'm just wondering how much of that, how wide of that of um how much they had to broaden the sensitivity and the spectral the spectral window. Is that a term?
Yeah, I think that's mentioned. So you're asking like how much sensitivity had to be brought based off of how far the objects can be seen. Is that so? I think yeah, that's why like the gold mirrors were used and everything else, like the JWST had like the big design, like the mirrors that can reflect a lot of light. So I think that was like fine tuned a lot until it was able to see like even like the very first galaxies because that's what made it the main difference between JWST and Hubble, as Hubble was like only able to see like a certain amount of galaxies, like only like in the toddler phase type of thing, but James Webb was able to peer even more into the distant past because of its gold mirrors.
Yeah.
Yeah, so I think yeah, that the sensitivity of JWST was like much more than the Hubble.
I'm kind of curious of whether it's looking at anything there that is blue shifted.
Blue shifted, yeah, I don't think so. I don't think it's gone that far. Yeah.
Well, red shifted objects are moving away from us. Blue
Right.
shifted objects are moving towards us. like the Andromeda Galaxy is supposed to be heading our way for a collision in the um, distant future.
Yeah, for blue shifted objects, I haven't heard of JWST looking at that, so I don't know if it has the capability to look through the blue shifted objects, but yeah, that might be like some sort of like future mission, like after JWST um gets all the data from the red shifted objects, there might be another telescope that goes to detect the blue shifted ones. But yeah, it's a good question. Yeah, I haven't heard of anything about that. If not, thank you so much, everyone, for joining.
Thank you, Arjun. That was an really informative, and I thoroughly enjoyed your piano playing. You are so talented. Oh my gosh. Your interpretation of the Star Wars thing was right on.
Yeah.
Great. I want to thank everybody for joining us today. Our next Cell Speaker Series event is going to be on Saturday, July 19th, same time, 11 a.m. Eastern Daylight Time. And it's going to be one of our favorite speakers, Owen Swart, from Region 8. He is an amazing speaker and works with cheetahs on the Cheetah Outreach Conservation Facility, and his talk is going to be on flagship species, how cheetah conservation drives biodiversity. If you were lucky to attend Project Earth, you would have heard a short presentation by Owen, and his topic is fascinating. We're working on bringing more terrestrial talks this year to Sol. So we've got a great lineup. We've got a few more slots to fill for the year, but appreciate you all joining. Please share the news about the Cell Speaker event with your chapters so we can continue to share this amazing world of science with all of you. Arjun, we're going to look forward to having you back again. You can count on that, and appreciate you taking your time today to share with us.
Thank you so much.
Thank you, Arjun. Appreciate it.